Hello, in this lecture I will explain what is mathematical induction. Uh, Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, etc. So we have actually two stages when we prove that something is true for all the natural numbers by mathematical induction. The first stage is actually to check that the statement, the equation, or the claim is true for n that equals to 1. And then, if it is indeed true for n that equals to 1, then we will move to the second stage. That is to say, we will assume that the statement is true for n, and as we rely on that assumption, we will prove that the statement is also true for n plus 1. So the first expression or equation will be the statement for n, or it is also called induction's hypothesis, or induction's assumption. So that will be our first equation. We assume that the statement is true for n, and then we will create the second equation that we must prove for n plus 1. Okay, we create the expression for n plus 1 that we must to prove that is true, and we will rely on the assumption that the statement is true for n in order to prove the statement for n plus 1. Okay, so I will repeat on the two stages. First of all, in the first stage, we check the statement is true for n that equals to 1. And then, if indeed the statement is true for n that equals to 1, then we will move to the second stage. That is to say, we will assume that the statement is true for n. That will be the first equation, and it is also called the hypothesis of the induction, or induction's hypothesis, or induction's assumption. And then we will create the second equation for that statement for n plus 1 that we must to prove, and we will prove it by relying on our assumption that the statement is true for n. Now I will explain the logic of mathematical induction, or what is behind mathematical induction, or what is the logic of mathematical induction. Actually, in the first stage, we checked that the statement is true for n that equals to 1. And then, if we indeed found out that the statement is true for n that equals to 1, then we actually know for sure that the statement is true for n that equals to 1. And then in the second stage, we actually proved that if the statement is true for n, then it must be true for n plus 1. So, in that way, we actually proved that the statement is true for all the natural numbers, and I will explain you why. First of all, we know for sure that the statement is true for n that equals to 1. And that is the first stage. We proved it in the first stage. We checked that it is true. And then in the second stage, we proved that in general, if it is true for n, it must be true for n plus 1. So in that way, we can say that we show for 100% that it is true for n that equals to 1, because we checked that it is true for n that equals to 1. And according to our general proof that if it is true for n, it must be true for n plus 1, we actually can say that we know that it is true for n that equals to 1, and according to our general proof, it must be true for n that equals to 1 plus 1. That is to say, it is true for n that equals to 2. And now we will repeat on the same process. Now we know for sure that it is true for n that equals to 2. And according to our general proof that if it is true for n, it must be true for n plus 1, then we know that because of the fact that it is true for n that equals to 2, it must be also true for n that equals to 2 plus 1. That is to say, it is true for n that equals to 3. And then we will again repeat exactly the same process. We know for sure that it is true for n that equals to 3, and for our general proof, we know that it is also must be true for n that equals to 3 plus 1, that is 4. So it is true for n that equals to 4. And then in the same process we will deduce that it is true for n that equals to 5, to 6, to 7, and so on. And actually in this way we proved that the statement is true for all the natural numbers, and that is what exactly we wanted to prove. Okay, so in order to clarify the issue, I will give you 2 examples. The first example will be 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So we must prove for all the natural numbers that this statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. Okay, we will start with the first stage. That is to say, we will check if the statement is true for n that equals to 1. Okay. So here we have only 1 because n equals to 1, so 1 equals to n times n plus 1 divided by 2, n equals to 1, so it is 1 times 1 plus 1 divided by 2. And here 1 plus 1 is 2, 2 times 1 is 1, all divided by 2, 1 times 2 is 2, divided by 2, 2 divided by 2 is 1. So 1 equals to 1. Okay, so we passed the first stage. We verified that this statement is true for n that equals to 1. So we can go to the second stage. That is to say, we will assume that this statement is true for n. That will be the first equation. 1 plus 2 plus 3 plus n equals to n times n plus 1 all divided by 2. So this way equation 1 will be the induction's hypothesis or induction's assumption is the same. So we assume that the statement is true for n, and from that assumption now we have to prove that this statement is true for n plus 1. That is to say, it is true for one plus 2 plus 3 plus n plus n plus 1, because we will create the statement for n plus 1. So in the last it will be n plus 1, all equals to, so in the original statement we have here n times n plus 1 divided by 2. So here for n plus 1, wherever it is written n in the original statement, we will write n plus 1, because we want to prove that the statement is true for n plus 1. So wherever it is written n, we will write n plus 1. So it will be, instead of n, we will write n plus 1. We open brackets, times n. So in the original statement we have n, and here we will write, instead of n plus 1 plus 1. So we will add to n plus 1 plus 1, all divided by 2. Okay, actually this is the second statement, the thing that we have to prove that the statement, the original statement, is true for n plus 1. So the expression for n plus 1 is 1 plus 2 plus 3 plus n plus 1 equals 2. Wherever it is written n in the original statement, we will write n plus 1. So it will be n plus 1. So in the original statement we have n times n plus 1 divided by 2. So for n plus 1 it will be n plus 1 times n plus 1 plus 1, because we want to write the expression for n plus 1. Okay, so now we have to prove, we assume that equation 1 is true, and we have to prove that expression 2 is also true. Okay, and as I've already said a couple of times, that we will rely on our assumption, or on our induction's assumption, that the original statement is true for n, and in that way we will prove that the second equation is true. Okay, as you can say here, this expression in the green color, it is exactly the same as this expression, and this expression equals to n times n plus 1 divided by 2. N times n plus 1 divided by 2. So actually we can substitute this expression in the green color by n times n divided by 2, because they are equal to each other. Okay, so we will do it now. So the second equation will be, instead of 1 plus 2 plus 3 plus n, we will write n times n plus 1 divided by 2, because they are equal to each other according to our assumption, the induction's hypothesis. Okay, because of the fact that they are equal to each other, we can substitute one by another. So it is n times n plus 1 divided by 2 plus, so in the second expression that we have to prove after the expression in the green color, we have n plus 1, so we will copy it to the second expression, n plus 1, all equals to n plus 1 times n plus 1 plus 1. So n plus 1 plus 1 is n plus 2. So we have here n plus 1 times n plus 2 all divided by 2. Okay, so the second, second expression, that is the expression we have to prove that is true. Okay, this is the expression for n plus 1. Okay, so actually we can divide the second expression for n plus 1 by n plus 1, because we have n plus 1 in both sides. Okay, so we will do it now. N times n plus 1 divided by n plus 1 will be n, all divided by 2, plus n plus 1 divided by n plus 1 is 1, equals n plus 1 times n plus 2 divided by n plus 1 is n plus 2, all divided by 2. So after we divided both sides of the equation by n plus 1, we have here n divided by 2 plus 1 equals to n plus 2 divided by 2. So we can separate n plus 2 to 2 parts. Okay, according to the rules, we will have n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2. Okay? Yes? So we separated n plus 2 to 2 parts. The first part will be n divided by 2 plus the second part 2 divided by 2. Okay? 2 divided by 2 is 1, so we will write it down. So we have here identity. The left part of the equation equals to the right part of the equation. So in this way we actually proved the equation for the statement for n plus 1. So we proved actually that if this statement is true for n, it must be true also for n plus 1. Okay? We assumed that this statement is true for n, and we actually proved that this statement is true also for n plus 1. Okay? And in this way we actually proved that this statement is true for all the natural numbers. Why? Because in the first stage we proved that this statement is true for n that equals to 1, because we checked that it is true, and it is indeed true for n that equals to 1. Okay? And in the second stage we proved that if this statement is true for n, it must be true for n plus 1 also. So in this way we proved that this statement is true for all the natural numbers, and I will explain you why. In the first stage we proved that this statement is true for n that equals to 1. And then in the second stage we proved that if this statement is true for n, it must be true for n plus 1 also. So we know for sure that this statement is true for n that equals to 1, and according to our general proof that if it is true for n, it must be true for n plus 1, we can say that because of the fact that it is true for n that equals to 1, it must be also true for n that equals to 1 plus 1. That is to say, it must be true for n that equals to 2. And now we will repeat on the same process. We know for sure that this statement is true for n that equals to 2. And according to our general proof that if it is true for n, it must be true also for n plus 1, we can say that because of the fact that it is true for n that equals to 2, it must be also true for n that equals to 2 plus 1. That is to say, it must be true for n that equals to 3. Okay, and we will continue again, we will repeat on the same process. We know for sure that it is true for 3. And according to our general proof that if it is true for n, it must be true for n plus 1, we can say that we know for sure that it is true for n that equals to 3. Therefore, it must be also true for n that equals to 3 plus 1, that is to say, for 4. And now we know that it is true for 4. And we will repeat on the same process in order to prove that it is true also for 5, for 6, for 7, for 8, and so on and so on. And so in this way, we actually proved that this statement is true for all the natural numbers. Okay? So I will give you a second example in order to clarify the topic. Second example will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n square times n plus 1 square all divided by 4. So we actually must prove, we have to prove that this statement is true for all the natural numbers. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. So we will start with the first stage. That is to say, we will check that this statement is true for n that equals to 1. Okay. So, in this side of the equation we will have 1 to the power of 3 equals, the other side, n squared times n plus 1 square all divided by 4, and we know that n is equal to 1, so n equals to 1, so it is n square, 1 square times 1 plus 1 square all divided by 4. So it is equals to 1 square is 1 and 1 plus 1 is 2, 2 to the power of 2 is 4, 1 times 4 is 4, divided by 4 is 1, so we got here that 1 equals to 1. So, as you can see here, we indeed verified that this statement is true for n that equals to 1. Okay, it is very simple, you can see. Here we have 1 to the power of 3 equals to n square is 1 square because n equals to 1, and n plus 1 is 1 plus 1 all squared and divided by 4, so it is 1 square is 1, 1 plus 1 is 2, so it is 1 times 2 to the power of 2 all divided by 4. 2 to the power of 2 is 4, so it is 1 times 4 all divided by 4, and 4 divided by 4 is 1, so 1 is equal to 1 because 1 to the power of 3 is 3, so 1 equals to 1. So we passed the first stage, the first test of the first stage. Now we will go to the second stage, and in the second stage we will actually assume that this statement is true for n, and we will prove it for n plus 1. So the induction's hypothesis will be that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So equation 1 is the induction's hypothesis or induction's assumption. We assume that this statement is true for n. That is to say, 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. So this is the induction's assumption. And as we rely on this assumption, we will prove that this statement is true for n plus 1. That is to say, we will create now the second equation. 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3. Here we have to prove for n plus 1, so we will add the numbers until we arrive to n plus 1, include n plus 1, because we have to prove for n plus 1 that this statement is true for n plus 1. And in the second side of the equation, wherever is written n, we will write n plus 1 because we want to prove that this statement is true for n plus 1. So here is written n squared, so we write n plus 1 squared. And then we have n plus 1 squared, so we write n plus 1 instead of n, and we will have n plus 1 plus 1, all squared. All divided by 4. So we have to prove that the second equation is true. And we will prove it exactly in the same way as we did in the first example. We will look on this expression, okay, we can say that this expression is exactly the same expression as the expression in the first equation. I actually paint the two expressions that are equal to each other in the green color, and as you can see in the first equation, the right side the left side of the equation equals to the right side. So this expression equals to this expression. 1 plus 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared all divided by 4. And this is according to our induction hypothesis. That's what we assume, that our statement is true for n. Okay, so we now rely on this assumption in order to prove that the second equation is true. So actually we can substitute 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3. We can substitute it by n squared times n plus 1 squared all divided by 4, because they are equal to each other according to our induction hypothesis. So we will do it now. Instead of 1 to the power of 3 plus 2 to the power of 3 plus n to the power of 3, we'll write n squared times n plus 1 squared. We can substitute it because they are equal to each other. N to the power of n plus 1 squared all divided by 4. And here we have n plus 1 to the power of 3. So we will leave it as it is. We will copy it as it is. All equals. Here we have n plus 1 squared times n plus 1 is n plus 2. So we will write n plus 1 squared times n plus 2 squared all divided by 4. So as you can see, this is actually the second equation that we must prove that it is true. And we actually have in this expression or equation n plus 1 square in both sides of the equation. So we will divide both sides of the equation by n plus 1 square. Okay. N squared times n plus 1 square divided by n plus 1 square equals to n square, all divided by 4, plus n plus 1 to the power of 3 divided by n plus 1 square will be n plus 1, n plus 1 square times n plus 2 square will divided by n plus 1 square will be n plus 2 square, and all divided by 4. Okay, so we divide this expression by n plus 1 square, so the result is n plus 2 square divided by 4. And here n plus 1 to the power of 3 divided by n plus 1 square is n plus 1, and n square times n plus 1 square divided by 4 all divided by n plus 1 square equals to n square divided by 4. So here we can multiply both sides of the equation by 4. And after we multiply it by 4, we'll get that n square divided by 4 times 4 will be n square, and n plus 1 times 4 is 4 times n plus 1, all equals n plus 2 square divided by 4 times 4 will be n plus 2 square. So we will open the brackets here. So after we opened the brackets, here is n square, and 4 times n is 4n, 4 times 1 is 4, and here n plus 2 square equals to n square plus 4n plus 4, like a plus b square, that equals to a square plus 2ab plus b square. Okay. So, as we developed expression 2 or equation 2, we got an identity. So in this way, we proved that the equation 2 is true. Actually, you can say that we proved that if this statement is true for n, it must be also true for n plus 1, because expression 2 is for n plus 1. So in this way we actually proved that this expression is true for all the natural numbers, because in the first stage we proved that this statement is true for n that equals to 1, And then in the second stage we prove that if it is true for n, it must be also true for n plus 1. So we can say that we know for sure that it is true for n that equals to 1, and according to our general proof that if it is equal to 1, it must be also equal, if it is true for n, it must be also true for n plus 1. We can say that we know that it is true for n that equals to 1, and therefore it must be also true for n that equals to 1 plus 1, because n equals to 1. So it is true for n that equals to 2. Okay, so we now know that this statement is true for n that equals to 2, and from our general proof that if it is true for n, it must be also true for n plus 1, we can deduce that because of the fact that we know that it is true for 2, it must be also true for 2 plus 1, that is to say for 3. So, and now that we know that it is true for n that equals to 3, it must be also true for 3 plus 1, according to our general proof. That is to say, it is true for 4. And we will repeat on the same process in order to prove that this statement is true for n that equals to 5 and 6 and 7 and so on and so on. So in this way we proved that this statement is true for all the natural numbers. Okay, so we can summarize the lecture and say that mathematical induction is a logical method to prove that a statement, an equation, or a claim is true for all the natural numbers. And natural number is a positive integer like 1, 2, 3, 4, and if we want to prove something according to mathematical induction, we will do two stages. In the first stage we will check that the statement, the equation, or the claim is true for n that equals to 1, and if it is indeed true for n that equals to 1, then we will go to the second stage. That is to say, we assume that the statement is true for n, and we will prove it for n plus 1. Okay, and the first equation that we will create will be the induction's hypothesis or induction's assumption, and then we will have to prove that it is true for n plus 1, so we will create a equation for n plus 1, and we will rely on our assumption in order to prove that the statement for n plus 1 is true. Okay, and after we proved that the second the statement is true for n plus 1, we actually proved that the statement is true for all the natural numbers, because of the fact that we actually proved it for we checked it that it is true for n that equals to 1. And according to our general proof that if it is true for n, it must be also true for n plus 1, we actually can say that we know for sure that it is true for n that equals to 1, and therefore, according to our general proof, it also must be true for n that equals to 1 plus 1. That is to say, it must be true for n that equals to 2, and we will repeat on the same process, and we will say that it must be also true for n that equals to 2 plus 1, that is to say for 3 and for 4 and for 5 and so on and so on. Okay, thank you very much.